It's a clear night, and you step outside, your eyes instinctively drawn upward. There, suspended in the inky blackness, is a sight both familiar and awe-inspiring. The moon, our celestial companion, hangs in the sky, a pale, glowing orb that has captivated humanity since time immemorial. This celestial body, Earth's only natural satellite, is more than just a nighttime spectacle. It's our constant companion in the vast cosmic ocean, silently orbiting our planet as it has done for billions of years. The moon has been a silent witness to the entire history of our species, from our earliest ancestors to the present day. Since the dawn of humanity, the moon has been a source of wonder, sparking our imagination and fueling our quest for knowledge. It has inspired countless myths and legends, guided sailors across treacherous seas, and marked the passage of time for ancient civilizations. Even in our modern era of space exploration and scientific understanding, the moon continues to fascinate us, beckoning us to unravel its mysteries. But what if I told you that this silent, seemingly passive observer plays a far more active role in our lives than you might think? Imagine, for a moment, a world without the moon. It might sound like the premise of a science fiction novel, but the reality is that without our lunar companion, life on Earth could be radically different. Consider this: the moon doesn't just control our ocean tides, it subtly orchestrates the very rhythm of life on our planet. From the migration patterns of animals to the blooming cycles of certain plants, the moon's influence reaches far beyond what meets the eye. And here's something even more intriguing. The moon might have played a crucial role in making Earth habitable in the first place. Its stabilizing effect on Earth's axis has helped maintain our planet's climate over billions of years, potentially creating the conditions necessary for life as we know it to evolve. Are you ready to embark on a journey that will reveal surprising secrets about our closest cosmic neighbor? Prepare to see the moon in a whole new light as we explore its formation, its features, and its profound impact on our blue planet. If this lunar introduction has piqued your curiosity and left you starry-eyed for more, don't forget to hit that like button. It's your way of signaling that you're gravitationally attracted to this content. And for more fascinating journeys through the cosmos, be sure to subscribe to our channel, Exploring the Universe. Together, we'll continue to unravel the mysteries of our solar system and beyond. The universe is vast, and our exploration has only just begun. The moon's diameter is approximately 3,475 kilometers. To put this into perspective, it's roughly 1/4 the size of Earth's diameter. If Earth were the size of a basketball, the moon would be about the size of a tennis ball. This relatively large size compared to its host planet makes the moon unique in our solar system. It's the 5th largest natural satellite and the largest in proportion to its parent planet. The average distance between the Earth and the moon is about 384,400 kilometers. This distance, however, isn't constant due to the moon's elliptical orbit. At its closest approach, the moon can be as near as 363,104 kilometers from Earth. At its farthest point, it can be as distant as 405,696 kilometers. To grasp this distance, consider this: if you could drive a car to the moon at highway speeds around 60 miles per hour, it would take you about 160 days to reach it. The moon's composition is primarily rocky, similar to Earth's crust but with some key differences. Its surface is covered with a layer of loose, fragmented material called regolith. This lunar soil is the result of billions of years of meteorite impacts that have crushed the moon's surface rocks into a fine, powdery substance. The lunar crust is composed mainly of oxygen, silicon, aluminum, calcium, and magnesium. Beneath the crust lies the mantle, and at the moon's core, scientists believe there's a small, partially molten iron core. One notable difference from Earth is the moon's lack of a substantial atmosphere and its absence of liquid water on the surface. These factors contribute to the moon's stark, barren appearance and its inability to retain heat, leading to extreme temperature variations between day and night. The origin of the moon has been a subject of scientific debate for centuries. Today, the most widely accepted theory is the giant impact hypothesis, also known as the Big Splash or the Theia impact. According to this theory, about 4.5 billion years ago, when the solar system was still in its infancy, a Mars-sized object collided with a proto-Earth. This catastrophic impact was so powerful that it ejected a massive amount of debris into orbit around Earth. Over time, this debris coalesced due to its own gravity, forming the moon we see today. This theory explains several observed phenomena: the moon's lack of a large iron core, the similarity in isotope ratios between Earth and moon rocks, suggesting a common origin, the moon's lower density compared to Earth, consistent with it being formed from the outer layers of the colliding bodies. Based on radiometric dating of moon rocks brought back by Apollo missions and subsequent studies, scientists estimate the moon's age to be about 4.51 billion years. This makes the moon almost as old as the Earth itself, which is estimated to be about 4.54 billion years old. This ancient age means the moon has been a constant companion throughout Earth's entire history. It has witnessed the formation of our planet's first continents, the emergence of life, and every significant event in our planet's long and complex history. The moon's formation and its subsequent evolution have played a crucial role in shaping Earth's own development. From stabilizing Earth's axial tilt to influencing our planet's tidal systems, the moon has been an integral part of Earth's story from the very beginning. Understanding the moon's characteristics and formation not only satisfies our curiosity about our nearest celestial neighbor, but also provides valuable insights into the early history of our solar system and the unique conditions that have made Earth habitable. Now that we've delved into some fascinating facts about the moon, let's take a moment to gauge your interest. If these lunar tidbits have made your curiosity wax like the full moon, why not give this video a lunar like? It's a stellar way to show that you're gravitationally attracted to this content. Just as the moon pulls on our oceans, let this content pull on your curiosity. By hitting that like button, you're not just showing appreciation. You're joining a community of space enthusiasts who are passionate about exploring the wonders of our universe. Your engagement helps our channel grow, allowing us to continue producing high-quality, educational content about space and astronomy. Remember, every like is like a tiny moonbeam, illuminating our path to create more videos that spark wonder and inspire learning. So, why not make your mark on our cosmic journey? One of the most captivating aspects of our celestial companion is its ever-changing appearance in the night sky. Let's explore the lunar phases and their significance. The moon's cycle of phases, also known as the synodic month, lasts approximately 29.5 days. This period represents the time it takes for the moon to complete one full cycle of phases as seen from Earth. It's important to note that this is slightly different from the moon's orbital period around Earth due to Earth's movement around the sun. During this phase, the moon is positioned between the Earth and the sun, with its unilluminated side facing us. The moon is essentially invisible from Earth during this time, as it rises and sets with the sun. About a week after the new moon, we see half of the moon's illuminated surface. It appears as a half moon in the evening sky, resembling the letter D. Approximately 2 weeks after the new moon, the entire visible surface of the moon is illuminated as seen from Earth. The moon rises at sunset and sets at sunrise. About a week after the full moon, we again see half of the moon's illuminated surface, but on the opposite side compared to the first quarter. It appears as a backwards D in the morning sky. Between these main phases, we observe transitional phases such as waxing crescent, waxing gibbous, waning gibbous, and waning crescent. The moon's phases have profoundly influenced human culture and timekeeping throughout history. Many ancient calendars, including the Islamic and Chinese calendars, are based on the lunar cycle. The concept of months originally derives from the moon's phases. Numerous celebrations and religious observances are timed according to lunar phases. For example, Easter in Christian traditions, Ramadan in Islam, and the Mid-Autumn Festival in Chinese culture are all determined by the moon's phases. Many traditional farming practices follow lunar cycles, with certain activities like planting or harvesting aligned with specific moon phases. The moon's phases correlate with tidal patterns, influencing fishing practices and coastal activities. The full moon, in particular, has inspired countless myths, legends, and superstitions across cultures, from werewolf tales to beliefs about its effects on human behavior. Even in our technologically advanced society, lunar phases continue to captivate us. They influence everything from crime rates to sleep patterns. To gain deeper insights into the moon's significance, we turn to Dr. Celine Silva, a renowned astronomer from the National Observatory. Dr. Silva shares her expert perspective. The moon serves as a natural laboratory for understanding the history of our solar system. Dr. Silva explains. Each crater, each lunar rock tells a story about Earth's past and the cosmos at large. The moon's surface, unlike Earth's, has remained largely unchanged for billions of years. Without atmospheric erosion or tectonic activity, the moon preserves a record of ancient events that have long since been erased from Earth's surface. Lunar craters are more than just scenic features. Dr. Silva elaborates, the size, depth, and distribution of craters on the moon's surface provide crucial information about the frequency and intensity of meteor impacts in the early solar system. This data helps us understand the conditions that Earth itself may have experienced during its formative years. When we analyze lunar rocks, Dr. Silva continues, we're not just studying the moon. We're gaining insights into the composition of the early solar system and, by extension, the materials that formed Earth. The Apollo missions and lunar meteorites have provided scientists with invaluable samples for study. Intriguingly, some scientists theorize that rocks ejected from Earth by ancient impacts may have landed on the moon. If found, these could provide unprecedented information about Earth's early history. The moon's story is interwoven with Earth's and that of the entire solar system. By studying the moon, we're piecing together the grand narrative of our cosmic neighborhood. One of the most significant ways the moon influences Earth is through its effect on our oceans. Let's explore how lunar gravity causes ocean tides and why these tides are so important. The moon's gravity exerts a pulling force on Earth. This force is strongest on the side of Earth facing the moon and weakest on the opposite side. This differential gravitational pull causes Earth's oceans to bulge outward on both the side facing the moon and the side opposite the moon. These bulges create high tides. As Earth rotates, different parts of the planet pass through these tidal bulges, resulting in the daily cycle of high and low tides. Importance of tides for coastal ecosystems. Tides play a crucial role in circulating nutrients in coastal areas, supporting diverse marine life. The regular flooding and exposure of intertidal zones create unique habitats for specialized plants and animals. Tidal patterns influence the distribution and behavior of many marine species, from algae to fish. Tides are vital for maintaining the health of estuaries, which serve as nurseries for many marine species. Tidal movements contribute to coastal erosion and the transport of sediments, shaping coastlines over time. These occur during new and full moons when the sun, moon, and Earth align. The combined gravitational forces of the sun and moon create higher high tides and lower low tides. These happen during first and third quarter moons when the sun and moon are at right angles to Earth. Their gravitational forces partially cancel out, resulting in less extreme tides. The difference between high and low tides is greatest during spring tides and least during neap tides. The alternation between spring and neap tides creates a dynamic environment that many coastal species have adapted to over millions of years. Understanding these tidal patterns is crucial for coastal construction, navigation, and fishing activities. The moon's influence on Earth extends far beyond tides. It plays a crucial role in stabilizing and affecting our planet's rotation. Let's explore these fascinating aspects. The moon acts like a stabilizer for Earth's rotational axis. Without the moon, Earth's axis would be subject to much larger variations over time. Earth's axial tilt is maintained within a narrow range due to the moon's gravitational influence. This stability is crucial for our climate and seasons. Some scientists suggest that without the moon, Earth's axial tilt could vary chaotically, potentially ranging from 0 to 85 degrees over millions of years. Such variations would cause extreme climate changes. The moon's stabilizing effect has likely contributed to the long-term climate stability necessary for the development of complex life on Earth. The gravitational pull of the moon causes a slight bulge in Earth's oceans. As Earth rotates faster than the moon orbits, this bulge gets slightly ahead of the moon. The moon's gravity pulls back on this bulge, creating a braking effect on Earth's rotation. This gradually slows Earth's rotation over time. Due to this tidal braking, Earth's day is getting longer by about 1.8 milliseconds per century. When dinosaurs roamed the Earth, a day was about 23 hours long. As Earth's rotation slows, the moon gradually moves farther away from Earth to conserve the system's angular momentum. This is the time it takes for Earth to complete one full rotation relative to the fixed stars, approximately 23 hours, 56 minutes, and 4 seconds. The solar day is the time it takes for the sun to return to the same position in the sky, which is about 24 hours. It's longer than a sidereal day because Earth moves along its orbit as it rotates. The difference arises because Earth orbits the sun while it rotates. Earth must rotate slightly more than 360 degrees for the sun to return to the same apparent position. Our daily timekeeping is based on the solar day, while astronomical observations often use sidereal time. Throughout history, the moon has captivated human imagination and played a significant role in shaping our cultures. Let's explore its diverse influences. Many cultures have associated the moon with gods or goddesses. Examples include Selene in Greek mythology, Chang'e in Chinese folklore, and Tsukuyomi in Japanese Shinto belief. The full moon is often linked to the transformation of humans into werewolves in European folklore. Many East Asian cultures see the shape of a rabbit on the moon's surface, contrasting with the man in the moon perceived in Western traditions. Various cultures have unique myths explaining lunar eclipses.
often involving cosmic battles or celestial creatures devouring the moon.
Many ancient civilizations based their calendars on the moon's phases. The Islamic calendar is a prominent modern example of a purely lunar calendar. Calendars like the Chinese and Hebrew calendars combine lunar months with solar years. The word month itself derives from moon, reflecting the historical importance of lunar cycles in timekeeping. Many religious observances, such as Easter in Christianity and Ramadan in Islam, are determined by lunar phases. The moon has been a popular subject in paintings, from Van Gogh's Starry Night to traditional Chinese landscape paintings.
Countless poems, novels, and stories feature the moon, from Shakespeare's plays to science fiction works like H.G. Wells' The First Men in the Moon.
The moon has inspired numerous songs across genres, from classical pieces like Debussy's Clair de Lune to pop hits like Walking on the Moon by the Police. The moon has been a central element in many films, from Georges Méliès' 1902 A Trip to the Moon to modern blockbusters like Moon. Lunar photography has become a popular hobby and art form, especially with the advent of powerful consumer telescopes and cameras. The moon has been a subject of human fascination for millennia, but it wasn't until the 20th century that we were able to begin exploring it directly. Let's delve into the history and future of lunar exploration. NASA's Apollo program, running from 1961 to 1972, was designed to land humans on the moon and bring them safely back to Earth.
On July 20, 1969, Neil Armstrong became the first human to step on the lunar surface, uttering the famous words, "That's one small step for man, one giant leap for mankind."
He was followed by Buzz Aldrin, while Michael Collins orbited above in the command module. Apollo 12, 14, 15, 16, and 17 also successfully landed on the moon, with Apollo 17 in 1972 being the last manned mission to date. The Apollo missions brought back 382 kilograms of lunar rocks, core samples, pebbles, and dust from the lunar surface. These samples have been invaluable for understanding the moon's composition and history. Clementine, 1994. This joint NASA-2D mission mapped the moon's surface in multiple wavelengths. Lunar Prospector, 1998 to 1999. NASA's orbiter that found evidence of water ice at the lunar poles. SMART 1, 2003 to 2006. The European Space Agency's first lunar mission, testing solar electric propulsion and searching for ice. China's ongoing lunar exploration program, including the first soft landing on the far side of the moon, Chang'e 4 in 2019. India's lunar exploration program, with Chandrayaan-1 confirming the presence of water molecules on the moon's surface. Artemis, 2010 present, NASA's twin spacecraft studying the moon's interaction with the solar wind. NASA's current initiative aims to return humans to the moon by 2024 and establish sustainable lunar exploration by the end of the decade. And planned small space station in lunar orbit to serve as a solar-powered communication hub, science laboratory, short-term habitation module, and holding area for rovers and other robots. Various space agencies, including ESA, JAXA, CSA, and others, are collaborating on lunar exploration plans. Companies like SpaceX, Blue Origin, and others are developing technologies for lunar missions and potential colonization. Long-term plans include establishing a permanent human presence on the moon, which could serve as a stepping stone for Mars exploration. Future missions aim to explore the possibility of using lunar resources to support long-term human presence and deep space missions. The moon's surface features a diverse array of geographical features, each telling a part of its 4.5 billion-year history. Lunar Maria. Maria are large, dark, basaltic plains on the moon's surface. These were formed by ancient volcanic eruptions, filling large impact basins with lava that later cooled and solidified. Maria cover about 16% of the lunar surface, mostly on the near side. Famous examples include Mare Tranquillitatis and Mare Imbrium. Maria are rich in iron and magnesium, giving them their darker appearance compared to the lunar highlands. Highlands, mountainous regions and craters. Lunar highlands are the light-colored, heavily cratered regions of the moon. They are generally several kilometers higher than the Maria. Highlands are primarily composed of anorthositic rocks, rich in calcium and aluminum. The highlands are densely packed with impact craters of various sizes, some over 1,000 kilometers in diameter. Notable mountain ranges include the Apennines, which rise up to 5 kilometers above the surrounding plains. The far side of the moon. Differences from the near side. The far side is the hemisphere of the moon that always faces away from Earth due to tidal locking. It was first photographed by the Soviet Luna 3 probe in 1959. The far side has significantly fewer maria than the near side, making it more heavily cratered and generally brighter.
This is one of the largest known impact craters in the solar system, spanning 2,500 kilometers and up to 13 kilometers deep.
The far side's crust is thicker on average than the near side, which may explain the lack of widespread volcanism. The far side is of great interest for radio astronomy as it's shielded from Earth's radio emissions.
The Moon provides us with a variety of fascinating celestial events and optical phenomena.
Let's explore some of the most notable ones. Lunar eclipse occurs when Earth passes between the Sun and the Moon, casting its shadow on the Moon. Total, Moon fully in Earth's umbra. Partial, part of Moon in umbra. And penumbral, Moon only in Earth's penumbra. During a total lunar eclipse, the Moon often appears reddish, known as a blood moon. Solar eclipse happens when the Moon passes between the Sun and Earth, blocking all or part of the Sun types. Total, Moon completely covers Sun. Partial, Moon covers part of Sun. And annular, Moon appears smaller than Sun, creating a ring of fire. Total solar eclipses are rare and spectacular events, revealing the Sun's corona. Supermoon occurs when a full moon coincides with the Moon's closest approach to Earth in its orbit. Appears up to 14% larger and 30% brighter than a regular full moon. Typically happens 3 to 4 times a year. Blue moon, traditionally defined as the third full moon in a season with 4 full moons. Modern definition: the second full moon in a calendar month. Occurs roughly every 2.5 years. Despite the name, the Moon doesn't actually appear blue. Librations, apparent oscillations of the Moon. Libration is the apparent wobbling of the Moon, allowing us to see slightly more than 50% of its surface over time. Longitudinal, east-west wobble due to the Moon's elliptical orbit. Latitudinal, north-south wobble caused by the tilt of the Moon's axis. Diurnal, daily libration due to Earth's rotation. Through libration, we can observe about 59% of the Moon's surface from Earth over time. Libration allows astronomers to study portions of the Moon's far side from Earth, aiding in mapping and research. The Moon serves as an invaluable record of the early history of our solar system, preserving evidence that has long since been erased on Earth. Impact craters form when asteroids or comets collide with the lunar surface. The size and shape of craters provide information about the impacting object and the collision's energy. Newer craters overlap older ones, allowing scientists to establish a relative chronology. The density of craters in an area indicates its age. More heavily cratered regions are generally older. The Moon's craters provide insights into the frequency and intensity of impacts in the inner solar system over billions of years. This information helps us understand Earth's early bombardment history. The Moon has no significant atmosphere, meaning there's no wind or rain to erode surface features. Unlike Earth, the Moon has no active plate tectonics to reshape its surface. The primary agents of change on the lunar surface are impacts and subtle effects from temperature variations. Features billions of years old remain largely intact, providing a window into the early solar system. The Apollo missions brought back 382 kilograms of lunar rocks, core samples, pebbles, and dust. These samples range in age from 3.2 billion to 4.6 billion years old. Rocks ejected from the Moon by impacts have been found on Earth, providing additional samples. Lunar samples have helped refine our understanding of the Moon's formation and evolution. They provide evidence for the giant impact theory of Moon formation. Lunar samples have been crucial in calibrating radiometric dating techniques used across geology. By studying the Moon, geologists gain insights into Earth's early history, much of which has been erased by our planet's dynamic processes. Upcoming missions aim to collect samples from previously unexplored areas, potentially revealing new chapters in lunar and solar system history. Throughout history, the Moon has been the subject of numerous myths, legends, and misconceptions. Let's explore some of the most common ones and their scientific explanations. The Moon is not made of cheese. This whimsical idea likely originated from the Moon's appearance, its cratered surface resembling a wheel of cheese. It gained popularity through folklore and children's stories. The Moon is composed primarily of rock and metal. Its crust is mainly made of oxygen, silicon, aluminum, calcium, and magnesium. The core is believed to be rich in iron and possibly some nickel. Lunar samples brought back by Apollo missions definitively proved the Moon's rocky composition. Spectroscopic analysis from Earth and space probes also confirm its mineral makeup. No proven relationship between lunar phases and human behavior. Many cultures associate the full moon with increased crime, accidents, and unusual behavior. Some believe the moon affects childbirth rates or mental health. Numerous studies have found no statistically significant correlation between lunar phases and human behavior.
Any perceived increases in odd behavior during full moons may be due to confirmation bias or increased visibility at night.
While the moon does affect Earth's tides, humans are not significantly impacted by these gravitational changes.
Some animals do exhibit behavior linked to lunar cycles, but this is likely due to changes in light levels rather than any mystical influence.
The moon doesn't have a dark side, only a far side. Many people believe that one side of the moon is always dark. The moon is tidally locked to Earth, meaning the same side always faces us. However, the side facing away from Earth still receives sunlight. The far side experiences the same day-night cycle as the near side, just at opposite times.
Dark side of the moon is a misnomer popularized by culture and media.
The correct term is far side or hidden side of the moon. The far side was first photographed by the Soviet Luna 3 probe in 1959. It looks quite different from the near side, with fewer maria and more craters. The moon's influence on our planet extends far beyond its nightly illumination of the sky.
It has played, and continues to play, a crucial role in Earth's habitability and the development of life.
Possible role in the origin of life. The moon's gravitational pull creates tides in Earth's oceans. These tides may have played a role in the formation of early biomolecules by concentrating organic compounds in tidal pools. The moon helps stabilize Earth's axial tilt, preventing extreme climate variations that could have hindered the development of complex life. Over billions of years, the moon has gradually slowed Earth's rotation. This slowing may have created more favorable conditions for life to evolve. Circulunar rhythms are biological cycles that correlate with the phases of the moon. Many marine animals exhibit lunar synchronized behaviors, particularly in reproduction. Examples include coral mass spawning events and the breeding cycles of certain fish species. Some insects, like the palolo worm, time their reproduction to specific lunar phases. Certain bird species may use the moon for navigation during migration. While controversial, some studies suggest subtle lunar influences on human sleep patterns and menstrual cycles, though more research is needed for conclusive evidence. Importance for navigation and agriculture throughout history. Ancient seafarers used the moon's position and phases for navigation. Lunar cycles were crucial in developing early calendars, essential for long sea voyages. Many traditional agricultural practices are based on lunar phases. The concept of planting by the moon's phases persists in some forms of organic and biodynamic farming. Lunar cycles form the basis of many ancient calendars, including the Islamic calendar still in use today. The word month itself derives from moon. Lunar cycles have been central to many cultural and religious practices throughout human history. Festivals and rituals in various cultures are often timed according to lunar phases. While less critical for navigation today, understanding lunar cycles remains important for predicting tides, which affects shipping and coastal activities. Lunar illumination levels are considered in military and search and rescue operations. The moon's influence on Earth and its life forms is a testament to the interconnectedness of our cosmic environment. From potentially aiding in the origin of life to shaping human culture and activities, the moon continues to play a vital role in our planet's story. As we look to the future of space exploration and potential lunar colonization, our understanding of this relationship will undoubtedly deepen, potentially revealing new insights about our place in the universe. As humanity's space exploration capabilities advance, the moon is increasingly seen as not just a scientific curiosity, but a potential resource and stepping stone for further space exploration. Potential for lunar resource mining. Deposits of water ice have been detected in permanently shadowed craters at the lunar poles. This could be used for drinking water, oxygen production, and rocket fuel. The moon's surface contains helium-3, a potential fuel for nuclear fusion reactors. While fusion technology is still developing, this could be a valuable energy source in the future. The moon may contain concentrations of rare earth elements used in electronics and renewable energy technologies. Developing economically viable extraction methods in the lunar environment. Addressing legal and ethical concerns about space resource utilization. NASA's Artemis program aims to establish a sustained human presence on the moon by the end of the 2020s. Other space agencies and private companies are also developing lunar base concepts. The lunar South Pole is a prime candidate due to its potential water ice deposits and areas of near-constant sunlight. Plans include habitation modules, power systems, and in-situ resource utilization facilities. A permanent base would allow for long-term lunar studies and astronomical observations from the Moon's surface. Radiation protection, dust mitigation, and psychological factors of long-term lunar living. The Moon can serve as a proving ground for technologies needed for Mars missions and beyond. If water ice can be mined and processed on the Moon, it could serve as a refueling station for deep space missions. The Moon's lower gravity makes it easier to launch missions to other planets or asteroids. Plans for a small space station in lunar orbit could serve as a staging point for missions to Mars and the outer solar system. Lunar-based telescopes could provide new insights into the universe, free from Earth's atmospheric interference. The Moon's role in Earth's past, present, and future offers a profound perspective on our place in the cosmos. If this video has made you want to observe the Moon with new eyes, don't forget to subscribe to the Exploring the Universe channel. Together, we'll continue our journey through the mysteries of our solar system and beyond.